Picture this: a distant world, billions of miles away, with a comet-like tail stretching across the void, its faint glow revealing a family tree of icy bodies frozen in time, each one a relic from the dawn of our solar system, linked by gravity and history, waiting to be unraveled by NASA's James Webb Space Telescope. In the vast, uncharted regions of the universe, where light takes millions of years to reach us, NASA's James Webb Space Telescope has made a discovery that could rewrite our understanding of how cosmic structures form. At the heart of this revelation is a family tree of distant objects, faint, ancient celestial bodies that share a common origin, linked by gravity and time. These objects, scattered across the cosmos, are not isolated wanderers but part of a larger, interconnected system, their relationships revealing secrets about the early universe. What makes this discovery so profound is that it's the first time scientists have mapped such a network of distant objects, using Webb's unparalleled sensitivity to peer into the cosmos' infancy. This chapter will explain what these objects are, how they were found, and why their family tree could reshape our view of cosmic evolution. To begin, let's clarify what these objects are. They are not stars or planets in the traditional sense, but rather distant, faint celestial bodies, some of which may be rogue planets, others perhaps remnants of ancient star clusters or even dark matter clumps. These objects are so far away that their light has traveled over 10 billion years to reach us, meaning we're seeing them as they existed when the universe was less than 1 billion years old. Their discovery is significant because they exist in regions of space where such objects are rarely observed, and their existence challenges existing models of how matter distributes itself in the cosmos. The key to understanding this discovery lies in the concept of a family tree. In astronomy, this term refers to the gravitational relationships between objects. Just as a family tree shows how individuals are related through ancestry, a cosmic family tree reveals how celestial bodies are connected through shared origins or gravitational interactions. For example, if two objects are part of the same system, they might have formed together or been pulled into the same region by gravitational forces. By tracing these connections, scientists can uncover the history of these objects and their role in the universe's evolution. The Webb telescope played a crucial role in this discovery. Unlike its predecessor, the Hubble Space Telescope, which primarily observes invisible and ultraviolet light, Webb is optimized for infrared wavelengths. This allows it to detect faint, distant objects that are too cold or too far away to be seen in other parts of the electromagnetic spectrum. By capturing infrared light, Webb can peer through the cosmic fog of dust and gas that obscures the early universe, revealing structures that were previously hidden. This capability was essential in identifying the newly discovered objects, which are so distant and dim that they would have been nearly impossible to detect without Webb's advanced instruments. The discovery process involved analyzing data from Webb's near-infrared camera, NRC, and mid-infrared instrument, MIRI, which are designed to capture images of faint, distant objects. Scientists used these instruments to scan regions of the sky where such objects are expected to exist, focusing on areas where gravitational lensing, a phenomenon where the gravity of massive objects bends and magnifies light from more distant sources, could amplify the signals. By combining these observations with computer simulations, researchers were able to identify patterns that suggested a network of interconnected objects. These patterns indicated that the objects were not randomly distributed but were part of a larger structure, possibly a star cluster or a group of dark matter clumps. One of the most intriguing aspects of this discovery is the implication it has for our understanding of dark matter. Dark matter, which makes up about 27% of the universe's mass, is invisible and interacts only through gravity. Its presence is inferred from the way it influences the motion of visible matter. The newly discovered objects, which may be clumps of dark matter, could provide clues about how this mysterious substance is distributed in the cosmos. If these objects are indeed dark matter clumps, their gravitational interactions could help scientists map the invisible scaffolding that holds the universe together. This would be a major breakthrough, as dark matter remains one of the greatest mysteries in astrophysics. Another significant finding is the potential link between these objects and the formation of the first galaxies. The early universe was a chaotic place, filled with gas clouds that eventually collapsed to form stars and galaxies. The newly discovered objects, which exist in regions where such processes are thought to have occurred, may have played a role in this formation. For example, some of these objects could be remnants of the first stars, which were massive and short-lived, or they could be the seeds of future star-forming regions. By studying their properties, scientists can gain insights into the conditions of the early universe and how galaxies evolved over time. The discovery also raises questions about the nature of rogue planets, planets that have been ejected from their home systems and now drift through space without a star. Some of the newly discovered objects may be such rogue planets, their faint infrared signatures indicating they are too cold to sustain fusion reactions but still retain heat from their formation. If these objects are indeed rogue planets, they could provide a new perspective on planetary formation and the prevalence of such bodies in the galaxy. Rogue planets are thought to be common, but their existence has been difficult to confirm due to their faintness and lack of a host star. Webb's ability to detect them could lead to a better understanding of how planets form and are distributed in the cosmos. The implications of this discovery extend beyond the study of individual objects. By mapping the family tree of these distant bodies, scientists can begin to piece together the larger structure of the universe. This network of interconnected objects may represent a kind of cosmic web, where dark matter and visible matter are intertwined in a complex dance of gravity. Understanding this web could help scientists predict how galaxies will continue to evolve, how dark matter influences the distribution of matter, and even how the universe will expand in the future. It's a glimpse into the underlying architecture of the cosmos, a framework that has shaped the universe since the Big Bang. However, the discovery is not without challenges. The faintness of these objects means that even with Webb's advanced capabilities, detecting them requires precise observations and sophisticated data analysis. Scientists must also account for the effects of interstellar dust and the limitations of their instruments. Additionally, the interpretation of these findings is still evolving. While the data suggests a family tree of interconnected objects, further research is needed to confirm their exact nature and relationships. This is where the role of the scientific community becomes vital. Collaboration between astronomers, physicists, and data scientists will be essential in refining these findings and exploring their broader implications. In conclusion, the discovery of these distant objects and their family tree represents a major step forward in our understanding of the universe. By using the James Webb Space Telescope, scientists have uncovered a network of celestial bodies that challenge existing theories and open new avenues of research. These objects, whether they are rogue planets, dark matter clumps, or remnants of the first stars, offer a unique window into the early universe and its hidden structures. As research continues, the family tree of these distant objects may reveal even more about the cosmos' origins, its hidden forces, and the intricate web of connections that bind the universe together. This discovery is not just about finding new objects, it's about unlocking the secrets of the universe itself. Imagine a vast cosmic family tree, its roots stretching back billions of years, its branches reaching across the universe. At the heart of this tree are the ancient objects we're now beginning to map, distant celestial bodies whose origins are as mysterious as they are profound. NASA's James Webb Space Telescope, with its unparalleled ability to peer into the infrared spectrum, has become the key to unraveling this cosmic lineage. But how did scientists arrive at this moment of discovery? What tools, methods, and collaborations made this possible? Let's trace the journey of how these distant objects were found, confirmed, and placed within the grand narrative of the universe's evolution. The story begins with the James Webb Space Telescope itself, launched in 2021 to succeed the Hubble Space Telescope. Unlike its predecessor, Webb is optimized for observing the faint, redshifted light of objects from the early universe. Its primary mirror, nearly 3 times larger than Hubble's, and its advanced instruments allow it to capture light that has traveled for over 13 billion years to reach us. But even with these capabilities, the process of discovering distant objects is not as simple as pointing the telescope at a patch of sky. It requires a combination of precise observation, cutting-edge technology, and a deep understanding of how light interacts with the cosmos. One of the first steps in this process is identifying potential candidates. Scientists use existing data from ground-based telescopes and earlier space missions to narrow down regions of the sky where ancient objects might exist. These regions are often in the direction of distant galaxies or near massive cosmic structures like galaxy clusters, which act as gravitational lenses to magnify the light of even more distant objects. Once a candidate is identified, Webb's instruments come into play. The telescope's near-infrared camera, NIRCam, and near-infrared spectrometer, NIRSpec, are critical tools in this phase. NIRCam captures high-resolution images, allowing scientists to detect faint, distant objects that are otherwise invisible. NIRSpec, on the other, breaks down the light from these objects into a spectrum, revealing their chemical composition and motion. This spectral analysis is crucial for determining not just what these objects are made of, but also how they're moving through space. But even with these powerful instruments, the data collected is vast and complex. The light from these distant objects is often faint and obscured by cosmic dust, requiring sophisticated processing techniques to extract meaningful information. Scientists use algorithms and machine learning models to sift through the data, identifying patterns and anomalies that might indicate the presence of new objects. This process is not without challenges. The light from these objects is redshifted due to the expansion of the universe, meaning that the wavelengths of their light are stretched into the infrared range. This redshift also means that the objects are moving away from us at incredible speeds, which further complicates the analysis of their spectra. To account for this, scientists must calibrate their instruments and models to correct for the effects of cosmic expansion, ensuring that their measurements are accurate. Once potential objects are detected, the next step is confirmation. This involves cross-referencing the data with other observatories and missions. Ground-based telescopes, such as the Very Large Telescope in Chile or the Atacama Large Millimeter Array, provide additional data points that help verify the findings. These telescopes can observe in different wavelengths, offering complementary information about the object's properties. For example, while Webb's NIRSpec can determine the chemical composition of an object, radio telescopes might reveal its motion or interactions with other celestial bodies. This multi-wavelength approach ensures that the discoveries made by Webb are robust and reliable. Another critical aspect of confirming these objects is their placement within the cosmic timeline. By analyzing the redshift of their light, scientists can estimate how far away they are and how long their light has been traveling to reach us. This redshift also provides insights into the universe's expansion history, helping to refine our understanding of cosmic evolution. For instance, objects with higher redshifts are generally older and farther away, offering a glimpse into the universe as it was in its infancy. However, interpreting this data requires careful calibration and comparison with theoretical models of the universe's structure and expansion. The process of mapping these objects' family tree involves more than just identifying their origins, it also requires understanding their relationships with other celestial bodies. This is where the concept of gravitational interactions comes into play. Some of these distant objects may have been influenced by the gravitational pull of nearby galaxies or dark matter structures, shaping their paths through space. By studying the motion and distribution of these objects, scientists can infer the presence of unseen mass or the influence of cosmic events like galaxy mergers. These interactions leave imprints on the objects' trajectories, which can be detected through careful analysis of their spectral data and spatial distribution. One of the most exciting aspects of this research is the potential to discover objects that challenge existing theories about the early universe. For example, some of these distant objects may have formed in environments that were previously thought to be impossible, such as regions with extreme temperatures or densities. By studying their composition and behavior, scientists can test the limits of current astrophysical models and refine our understanding of how stars, galaxies, and even planets formed in the early cosmos. These discoveries often lead to new questions, driving further exploration and innovation in observational techniques. The collaborative nature of this work is another key factor in its success. The James Webb Space Telescope is a product of decades of international collaboration, involving scientists, engineers, and institutions from around the world. This same spirit of cooperation extends to the analysis and interpretation of the data. Scientists from different disciplines, astrophysics, cosmology, planetary science, work together to piece together the story of these distant objects. Their expertise ensures that the findings are not only technically sound but also rich in context, connecting the discoveries to broader questions about the universe's history and future. As the research progresses, the implications of these findings continue to unfold. The family tree of these distant objects may reveal new insights into the distribution of dark matter, the formation of the first galaxies, or even the presence of primordial black holes. Each new discovery adds another branch to the cosmic tree, expanding our understanding of the universe's structure and evolution. However, the journey is far from over. The vastness of the cosmos means that there are still countless objects waiting to be discovered, each with its own story to tell. In the end, the process of exploring these distant objects is a testament to human ingenuity and perseverance. It is a reminder that the universe is not just a collection of stars and galaxies, but a dynamic, evolving system shaped by forces we are only beginning to comprehend. Through the lens of the James Webb Space Telescope, we are not just observers of the cosmos, we are participants in a grand, ongoing story, one that continues to unfold with every new discovery. NASA Webb explores family tree of newly discovered distant objects. This part of our deep dive into NASA Webb explores family tree of newly discovered distant objects focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For millennia, humanity has gazed at the night sky, tracing the paths of stars and planets, but it wasn't until the 20th century that we began to unravel the secrets of the cosmos in earnest. The discovery of distant objects, asteroids, comets, and rogue planets has always been a cornerstone of astronomy, but our ability to study them has evolved dramatically over the decades. From the first telescopes that peered beyond the moon to the launch of space-based observatories, each breakthrough has expanded our understanding of the universe. Today, NASA's James Webb Space Telescope is pushing the boundaries further than ever before, uncovering the family tree of newly discovered distant objects that could reshape our view of the solar system's origins. But to appreciate how far we've come, we need to look back at the milestones that made this moment possible. The story begins in the early 1900s, when astronomers like Edwin Hubble began to realize that the universe was far larger than previously imagined. Hubble's observations of distant galaxies in the 1920s revealed that the universe was expanding, a discovery that laid the foundation for modern cosmology. However, studying objects beyond our solar system remained a challenge. Ground-based telescopes were limited by Earth's atmosphere, which distorted light and made it difficult to observe faint, distant objects. It wasn't until the 1960s and 1970s that technology began to change this. The development of infrared astronomy, which allows us to peer through cosmic dust and detect cooler, fainter objects, marked a turning point. Instruments like the Infrared Astronomical Satellite, IRAS, launched in 1983, were the first to systematically survey the sky in infrared, revealing previously unseen objects such as distant galaxies and cold asteroids. The 1990s brought another leap forward with the launch of the Hubble Space Telescope. Orbiting above Earth's atmosphere, Hubble provided unprecedented clarity, capturing images of distant galaxies and helping scientists measure the universe's expansion rate. But while Hubble excelled at visible and ultraviolet wavelengths, it struggled with infrared observations, which are crucial for studying the coldest and most distant objects. This gap in capability was addressed in the 2000s with the launch of the Spitzer Space Telescope, which operated in the infrared range. Spitzer's discoveries included the detection of exoplanets, the study of star-forming regions, and the identification of distant galaxies that existed just a few 100 million years after the Big Bang. These missions demonstrated the power of infrared astronomy, but they also highlighted the need for even more advanced technology to probe deeper into the cosmos. The James Webb Space Telescope, launched in 2021, represents the culmination of decades of innovation. Designed to build on the legacy of Hubble and Spitzer, Webb is the most powerful infrared telescope ever built, with a mirror 2.4 times larger than Hubble's. Its ability to detect faint, distant objects has already revolutionized our understanding of the early universe, revealing the first galaxies to form after the Big Bang. But Webb's capabilities extend beyond the distant past. It is also being used to study objects within our own solar system. The discovery of new distant objects, such as those in the Kuiper Belt or the scattered disk, has long been a fascination for astronomers, but the tools to study them in detail were limited until now. These objects, often referred to as distant trans-Neptunian objects, are remnants from the early solar system, and their study could provide clues about how the planets formed and evolved. The concept of a family tree for these distant objects is a relatively new idea, but it builds on centuries of astronomical inquiry. The idea that objects share a common origin is not new. It has been applied to asteroids, comets, and even planets. For example, the Trojan asteroids that share Jupiter's orbit are believed to have formed from the same primordial material. Similarly, the study of comets has shown that many share similar compositions, suggesting they may have originated from the same reservoir in the outer solar system. However, the discovery of new distant objects has raised new questions about their relationships. Are these objects part of a single family, or are they the result of multiple distinct processes? Webb's advanced infrared instruments are now allowing scientists to analyze these objects in ways that were previously impossible, revealing their chemical compositions, orbital dynamics, and potential connections to one another. The journey to this point has been shaped by a series of technological and scientific breakthroughs. In the 1980s, the development of cryogenic detectors and more sensitive infrared sensors enabled astronomers to study faint objects with greater precision. These advancements were critical for missions like Spitzer, which operated at extremely cold temperatures to minimize thermal noise. The 1990s saw the refinement of these technologies, leading to the creation of more sophisticated instruments capable of capturing detailed data across a broader range of wavelengths. By the 2000s, the field of infrared astronomy had matured, and the scientific community was ready for a new generation of observatories. The James Webb Space Telescope was conceived as a direct response to these needs, with its design optimized for infrared observations and its location in space ensuring minimal atmospheric interference. One of the key challenges in studying distant objects has always been their faintness and the vast distances involved. The farther an object is, the more its light is stretched into the infrared spectrum, making it harder to detect with traditional telescopes. Webb's advanced infrared instruments are designed to overcome this challenge. Its near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, can capture detailed images of these objects even when they are billions of light-years away. Additionally, Webb's spectrograph allows scientists to analyze the chemical composition of these objects, providing insights into their origins and evolution. For example, by studying the spectra of newly discovered distant objects, researchers can determine whether they contain materials similar to those found in comets or asteroids, helping to piece together the puzzle of the solar system's formation. The discovery of these objects has also been aided by advances in computational power and data analysis techniques. In the past, identifying new distant objects required painstaking manual analysis of telescope images, but modern algorithms and machine learning tools have made the process much faster and more efficient. These tools can detect subtle patterns in the data, helping astronomers identify objects that might have been missed in earlier surveys. This has led to the discovery of numerous new distant objects, many of which are now being studied in detail using Webb's capabilities. The family tree concept is emerging from this wealth of data, as scientists begin to map the relationships between these objects based on their orbits, compositions, and other properties. The implications of these discoveries extend beyond our solar system. By studying the relationships between these distant objects, scientists can gain insights into the processes that shaped the early solar system. For example, if multiple objects share similar orbital characteristics, it could suggest they originated from the same parent body that broke apart. This would provide direct evidence of how planetary systems form and evolve, a question that has long been central to astronomy. Additionally, the study of these objects could help us understand the distribution of materials in the early solar system, shedding light on the conditions that led to the formation of planets and other celestial bodies. As we look to the future, the discoveries made by Webb and other missions will continue to shape our understanding of the universe. The family tree of these distant objects is just one part of a broader story of cosmic evolution, and each new discovery brings us closer to answering fundamental questions about our place in the cosmos. The journey to uncover these secrets has been long and complex, but it is a testament to the power of human curiosity and the relentless pursuit of knowledge. With each new mission, we are not just observing the universe, we are rewriting its story. As the James Webb Space Telescope peers deeper into the cosmos than ever before, it has uncovered a family of distant objects that challenge our understanding of the universe's earliest days. These objects, scattered across the vast expanse of space, are not just isolated points of light but potential members of a cosmic family tree, one that scientists are only beginning to unravel. Yet, despite the groundbreaking discoveries, many questions remain unanswered. What are these objects truly? How did they form? And what do their existence and relationships tell us about the universe's origins? The answers lie in the mysteries that still shroud these distant worlds, and the scientific community is only just beginning to grasp their significance. One of the most pressing questions revolves around the origins of these objects. While the James Webb Telescope has captured their faint glow, the details of their formation remain elusive. Are they remnants of failed stars, known as brown dwarfs, or perhaps rogue planets that drifted away from their birth systems? Some scientists speculate that these objects may have formed in the chaotic early days of the universe, when primordial gas clouds collapsed under their own gravity. However, the conditions of that era were so extreme that it's difficult to determine whether these objects emerged from such processes or if they were born in a different way altogether. The lack of definitive data means that their origins are still a subject of intense debate. Could they have formed in isolation, or did they originate from a larger system that has since been disrupted? These uncertainties highlight the complexity of studying objects so far removed from our own solar system. Another layer of mystery lies in how these objects are connected. The term family tree suggests a relationship, but what exactly binds these distant entities together? Some researchers believe they may share a common origin, perhaps as part of a larger system that was torn apart by gravitational forces. For instance, if these objects were once part of a binary star system or a cluster of stars, their trajectories might still carry echoes of that past. However, the vast distances between them make it challenging to trace such connections. Scientists are using advanced techniques like spectroscopy and gravitational lensing to analyze their composition and motion, but even these methods have limitations. The light from these objects has traveled billions of years to reach us, meaning we are seeing them as they were in the distant past. This time delay complicates efforts to determine their current state, leaving room for speculation about their true nature and relationships. The classification of these objects also remains a point of contention. Some appear to be dim, cool celestial bodies that defy easy categorization. Are they brown dwarfs, which are sometimes called failed stars because they lack the mass to sustain nuclear fusion? Or are they rogue planets, wandering through space without a host star? The distinction is not merely academic, it has profound implications for our understanding of planetary formation and the distribution of matter in the universe. For example, if these objects are rogue planets, their existence could suggest that planetary systems are more dynamic than previously thought, with planets being ejected from their birth systems due to gravitational interactions. However, without more precise data on their temperatures, compositions, and movements, scientists are left to make educated guesses. The James Webb Telescope's ability to detect faint infrared signatures has provided valuable insights, but the full picture is still emerging. The implications of these discoveries extend beyond the objects themselves. If these distant entities are indeed part of a cosmic family, their existence could shed light on the early structure of the universe. For instance, the distribution of these objects might hint at the presence of unseen mass, dark matter, that influences their motion. Alternatively, their formation could challenge existing models of star and planet formation, suggesting that processes in the early universe were more varied or chaotic than previously assumed. Some scientists even propose that these objects could be remnants of the first stars, which were massive and short-lived. If so, studying them might provide a window into the conditions of the universe just a few 100 million years after the Big Bang. Yet, these ideas remain speculative, and more data is needed to confirm or refute them. One of the most intriguing aspects of this research is the role of gravitational interactions in shaping the trajectories of these objects. If they are part of a family, their paths might be influenced by the gravitational pull of unseen bodies or by the remnants of their original systems. For example, if these objects were once part of a cluster of stars, their current positions could be the result of a supernova explosion or a close encounter with another massive object. However, the sheer scale of the universe makes it difficult to trace such events. The James Webb Telescope's ability to observe distant galaxies and their structures has provided some clues, but the full story of these objects' movements remains incomplete. Scientists are also exploring whether these objects could be part of a larger network of dark matter clumps, which might have influenced their formation and distribution. The scientific community is divided on how to interpret these findings. Some researchers argue that the family tree concept is a useful framework for understanding the relationships between these objects, while others caution against overinterpreting the data. For instance, the term family might be metaphorical rather than literal, suggesting that these objects share certain properties rather than a direct lineage. This debate reflects the broader challenge of studying objects that are so far away and so faint. Even with the James Webb Telescope's advanced capabilities, there are limits to what can be observed. The telescope can detect the light from these objects, but it cannot directly measure their mass or composition with absolute certainty. As a result, scientists must rely on indirect methods, which can lead to multiple interpretations of the same data. Another layer of uncertainty lies in the timeline of these objects' existence. The light we see from them has traveled billions of years to reach us, meaning we are observing them as they were in the distant past. However, this also means that their current state may have changed significantly. For example, if these objects are young, they might still be in the process of forming, while older ones could have evolved into different types of celestial bodies. The James Webb Telescope's ability to peer through cosmic dust and capture infrared light has allowed scientists to study these objects in greater detail, but the full story of their evolution remains unclear. This temporal disconnect adds another dimension to the mystery, as scientists must piece together the history of these objects based on snapshots from the past. The search for answers is ongoing, and new discoveries are likely to reshape our understanding of these distant objects. For example, future observations might reveal more about their chemical compositions, which could provide clues about their origins. Alternatively, the discovery of additional objects in the same region of space could help establish patterns or relationships that were previously hidden. The James Webb Telescope's mission is not just about finding new objects but about understanding the broader context in which they exist. By studying these distant entities, scientists hope to gain insights into the processes that shape the universe in its infancy and the forces that continue to influence its evolution. In the end, the story of these newly discovered objects is one of mystery and possibility. They represent a glimpse into the early universe, a time when the cosmos was still young and its secrets were largely unknown. While the James Webb Telescope has provided valuable data, the questions it raises are as vast as the space it observes. The scientific community continues to explore these mysteries, driven by the desire to uncover the fundamental truths about the universe. As researchers refine their methods and gather more data, the family tree of these distant objects may become clearer, but for now, they remain a testament to the enduring curiosity that drives humanity to look beyond the stars. NASA Webb explores family tree of newly discovered distant objects. This part of our deep dive into NASA Webb explores family tree of newly discovered distant objects focuses on explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. So, what did we just uncover? Let me break it down. First, NASA's James Webb Space Telescope has identified a family of distant, icy objects orbiting the Sun, some of the most ancient remnants from the early solar system. These objects, scattered in the outer reaches, share subtle orbital similarities, suggesting they're gravitational cousins, possibly even siblings, bound by shared origins. Second, their discovery challenges our understanding of how the solar system formed. These icy bodies, some with orbits tilted or stretched in unusual ways, hint at a chaotic early history where collisions and gravitational tugs reshaped the architecture of our planetary neighborhood. Third, the Webb telescope's ability to peer so far into the cosmos, beyond the reach of previous instruments, has revealed these objects in unprecedented detail, offering clues about the primordial material that coalesced into planets. But here's the kicker: some of these objects might not have originated in our solar system at all. Their peculiar trajectories suggest they could be interlopers from another star system, swept into ours by cosmic encounters. This isn't just about finding new worlds, it's about rewriting the story of how our solar system evolved. These icy wanderers are like time capsules, preserving the fingerprint of the past. By studying their family tree, how they're related, how they moved, how they've interacted, we're peeling back layers of history. For instance, their orbits might reveal the gravitational influence of unseen planets, or even the remnants of a long-lost dwarf planet. And the Webb telescope's infrared vision is key here. It can detect the faint heat signatures of these distant objects, even when they're shrouded in darkness. This technology is allowing us to map the solar system's hidden architecture, uncovering a family tree that's been waiting millennia to be discovered. But the implications go deeper. If these objects are truly outsiders, it suggests our solar system has had more cosmic collisions than we ever imagined. It's a reminder that the universe is a dynamic, interconnected place. These findings don't just expand our knowledge, they force us to rethink the very foundations of planetary science. So, what's next? The Webb telescope isn't just looking at the past, it's peering into the future. By tracking how these objects move, scientists can predict their paths, potentially identifying ones that might one day cross the orbits of the inner planets. And while we're at it, we're also searching for signs of ancient impacts that might have influenced Earth's history. But let's not forget, this is just the beginning. The data from Webb is still being analyzed, and more discoveries are waiting in the vast, uncharted dark. If you've enjoyed this deep dive into the family tree of distant worlds, hit that subscribe button for daily explorations of the cosmos. And if you have a theory about these icy wanderers or a question about their origins, drop it in the comments, we're always curious to hear your thoughts. The universe is full of mysteries, and every new discovery brings us one step closer to understanding our place in it.